Yes, hello guys, let's start now. We are starting recording. We are continuing with chapter 4, which will be about pumps. Last time we finished the parallel pipes and pipes connected in series, which was chapter 3. So now we come to pumps. So what are the pumps? Let's just open a discussion first and then we can go. So what are the pumps? It is a mechanical device that is used to pump water, let's say, simply. But when we need to pump water, what is the idea of using it? One of the usage of pumps, water pumps, is to, for example, if we have here a reservoir, and we have a reservoir that is, or let me give you a simpler example. If we have a building like this, so these are just the stories, okay? So one of the things we do normally is pumping water from the bottom up to the tank, which is located at the roof, isn't it? So for example, this is the pipes. So we are pumping water from here using a pumping device to pump water from that place, from the tank that is available down here. Because here, for example, we have water, we are pumping the water to the tank there, so that we can use the water for normal houses. So what does it mean in hydro and in other terms? If that is the source A and that is the end B, so we can say when head A is less than head B. Because if we take as a datum, for example, head A is 2 meters, just 2 meters above the surface, or maybe more, doesn't matter, maybe 2 meters, while head B is height of the building. Maybe height of the building is, let's say, 3, 1, 2, 3, 4, 5. So 5 by 3 is 15 meters, for example. More than 15, it will be 17 meters. So 2 meters in normal condition, if we were not having pump and only just connecting the pipe directly, water will not go out, and go up to that floor, because there is no pump. It can't, and this head of A cannot overcome that. Otherwise, actually, what we can observe is that water will come from there down. Water will come down, but we put certain devices to not let that water go down. Anyway, so we put a pump. So that is one usage of the pump, okay? We can see that is the usage of the pump. Another usage of pumps is normally what we can say about that. Yes, another usage of the pump is to use a pump there. I just make this one small, like this. For what reason? For example, we are taking the water from the tank, but while it is going, yes, let me put it here, so that while the water is going from here to the flats here, anyhow, let's do that inside the flats. Okay, so this one, what it will make? It will make the water faster. So two reasons to use the pumps, which is, first one is to overcome the head difference, which means in normal condition it can't go, or if we draw a simpler, water can't go up if the other reservoir is there. It can't go up to that reservoir if there is no pump. If there is no pump, it can't go there unless we put a pump on the device, so that water now can flow in that direction. So that is one usage. And the other one, which is in normal case, just you want the water to be faster, so you can open the pump. So this is the second reason. This is our second reason. And that is the first reason. Okay, so that's it. Let's continue the other things. So now what we need to study is how that will affect our solution, how it will affect our solution, and how we can combine the pumps in the solution in our hydro problems. Okay, then the thing is that how to combine it, as we said, when the head it is like this, as I gave you this example. What we write, if we want to write the Bernoulli equation, for example, from this head going all up to that tank surface, water surface, for sure this tank will be bigger, something bigger we can just select and make it bigger as a tank. Anyway, fill it with water. But think of it, it's like this, yeah. Okay, so that is the water tank. So as I said, if we write the equation between A and B, we will end up with head A equals to head B plus summation of the head losses. And this one, we said it's normal condition, the calculator will give you error because you are saying 2 meters equals to 17 plus, still you are adding plus 17, and this plus should change to minus in order to make the equality between 2 and 17, and we can do that equality, therefore it will give you error at the end. So what we can do is that we are adding a pump, so head at A plus head of the pump. Forget about that pump, by the way. Let's discuss this pump. So plus head of the pump. This is the addition that we make. Head of the pump should be equals to the rest. So what this head of the pump will try to do is that it will try to make this one on the left greater, so that it can overcome the difference. Yani the head of the pump now required should be minimum 15 meters. How I know that it's 15? Because 2 plus something head pump equals to 17, and there is a still plus. So what I say is minimum 15, because if there is no losses, if losses were 0, head of the pump, how much it should be? 15 meters. So that is if just imaginary, if we are saying the flow is ideal. You know, we took that thing. If a flow is ideal, here we can write just ideal in case of an ideal flow, and we for sure our flow is not ideal, therefore you should what, that's why we are saying minimum. Yani we can write it here, it should be greater than 15 meters head of the pump. So that's it. That is how we can directly understand how much we need for the head of the pump. So that this is how we can add it. So we add it to the left plus. Okay. So now coming to the curve, what is about the curve? Sometimes it's one way of solving the pump problems is to get the curve of the pump. Normally all the pumps will have curves. It will have table given on that given there, I mean in the pump, on the pump, and that curve, if we draw it, it will be something like this one, the blue one. Okay, the blue one with this point at the, by the way, this one, the HP, it's not the dot, it is just the y-axis. Y-axis is head of the pump, and x-axis, let me just try to make this one smaller, and x-axis is the Q. Okay, so it's like this. This point here, we call it shut off head, which means there is no discharge. It's only the maximum height of the pump, but there is no water delivery. Okay, there is no water delivery. So what about this one? That one, which means at Q equals to 0. At Q equals to 0. This point is at HP equals to 0. So we can say about this point, pump is not doing any work, and yes, pump is not doing any work, and water is just directly delivered So pump, if if it is working or not, same discharge we are getting. So pump is not doing anything, that is the thing. So what is the point of the curve? The point or the aim of the curve, we say that aim of the curve is the following. When we have the curve, for example like this, and I have this pump curve, okay, the aim is that here HP, it is just a way of solving, and we wrote the Bernoulli equation, okay, and when we wrote the Bernoulli equation, we discovered that head of the pump is unknown and Q will be unknown too. We don't know both. So in one equation we have how many unknowns? 2 unknowns. This is two unknowns, isn't it? 2 unknowns. And 2 unknowns, we cannot write any other equation, same as the parallel pipes, because I'm telling you about normal question. There is no parallel pipes, there is no continuity equation needed, nothing. So how we can solve it? What we can say is that here already there will be the axis number, so 1, 2, for example, 3, 4, 5, 6, like this. Okay, so that's, for example, 10 is gonna be 10, 20, like that, 10, 20, 30, and it goes so on. So we can assume one of them, which is 30, for example. I can assume 30, and that I will call it trial 1. I'm trying to just explain it step by step so that we can understand together how we can solve it. So I can say Q, it's gonna be 30, assumed. 30, by the way, liters per second. So, and I can write it is assumed. Okay, assumed 30. Then try to solve the Bernoulli equation. Solve 1. We can write solve 1. Solve equation 1 for what? For HP, which is head of the pump. Okay, after we solve it and get the answer, we can go in then and check. We make a line, for example, at 30 and check how much is HP. For example, HP, it became here. So the point, our point, and just make it smaller. Okay, so that is our point here. Is it on the curve? No, it's not on the curve. It's under the curve. We say point under the curve. Okay, what I should do then? I should increase the discharge. For example, I would increase it to 40. This is just an example, okay? So I would say then trial 2 will be assuming Q is 40. Okay, then after that again solve for HP and see what is the answer. So you set point under the curve. All these just make it black or leave it as it is. Okay, solve for HP. Again we solved, and then after we checked, now the point is just slightly above the curve. So this is by trials. We will do these trials and you will see. So now the point is just what? Just above the curve a bit. Okay, so what I should say now? Point above the curve. So I can say reduce this Q a bit. How we can say trial 3? We can say it will be 35 liters per second. I am just assuming, or not 35, maybe I can say 36, like that. And look for 36, it will be somewhere here. This 36. and after we solve for 36, directly the point, for example, now the point is on the curve. Now the point is on the curve, and that is the point we are looking for. Okay, after we solve for HP. So this is how we solve it. That is the point. In trial 3 I assumed and then solved it for HP. Now HP is touching the curve, so all this I can make it green. By the way, what we can notice is that while we were solving these points, if we connect them, it will be something like this, a curve. So what we call this curve, let me just make it thin, I don't want it to be that much. This curve, if we make it a dashed, this curve we can call it what? Operating curve, which is the Bernoulli equation curve, to be honest. Okay, just let me copy this. Okay, so we call it operating curve. So if we have a program, for example, and we can plot this one, we can plot the Bernoulli equation itself, then it will be so easy to just find the answer, because it's the intersection point between operating curve and pump curve. Okay, but because we can't do this in exam, we don't have a program, that's why we should do it by trials. But sometimes if you can, because now you would ask this, if we can somehow know what points I should assume, which points we should assume, it would be easier to directly get the answer. But for example, you assumed one point, it was let's see, one point it was here and the other point it was there, like this above, so you can take two numbers. Don't make a straight line, between them, no, but try to say, for example, it will go something like this. Okay, or even the other point, if the point is here somehow, you can say I'm going like this, so I'm expecting, like this. So I am expecting to point to be somewhere here. So it is like 38 or 39. Okay, just as a trial. I know it's not easy. There is no way to make sure, because sometimes the first point, maybe even you draw first point and you say now, oh, this is the intersection point and I can expect it to be here. You don't know, because sometimes the second point may be so close to this one, and the point after it is like here, and the correct answer is here, is there, for example. So it is like at how much? At 40 or even more. Even sometimes maybe this point is really so close to each other, like this, and the other one like that, and the other one more farther, it's there. So what you understand from this, each case it's different. We can't know how the curve it is. Like sometimes the operating curve is going like this, maybe it's sharper like that, maybe it's directly like this, about to be vertical. So each will give you different. We don't know which Bernoulli is given, which system is given, because each red, this one for example, let me make it green, and the other one gray. So the gray one is for another system, green one is to another system. Each system, it has a unique or special curve. Okay, but this is the only hint we can do. Some students, they say, why not to assume HP, head of the pump, and then solve for Q in the question. Actually it can be somehow, but we don't do it. Somehow we don't do it. Okay, so we prefer to solve it assuming the Q then, because even if you assume HP, you can't know the F friction. You will see now later. So for F friction and like that, assuming Q is more reasonable, so that you don't need trials for F that much. Okay, here there is no trials. I will show you how I mean there is no trials. That's it. Some students even sometimes they are saying, why not to take a 1 point that is like this. Forget about these. They are saying here, for example, I have HP, it is 8 meters, so why not to choose this point and the point 40. No, not the curve, not on the curve. Then let's make this one lower. I'm now assuming only, okay? This point is 8 meters. So they are saying, why not we are choosing that point which is on the curve already. This point, it is on the curve, and saying HP is equal to 8 and Q is equal to 40. We are saying life is not easy that much. This is not correct at all. Why? Because this point you chose, this point they are talking about, this one I know it's on the curve, but we didn't check the Bernoulli equation. We didn't see the system picture even. You didn't see how the reservoir it is going, pipes, maybe after that we are having a parallel pipe, then pump is here, reservoir is there, or something else, any other picture. So you didn't test the system, and you are just taking randomly. This is, we call it a random selection of points. You just took a point. Maybe I would come and tell you, let's take the 50 then, or let's take the point at 30 and take the H to be 10, for example. Why not to choose that point? There is no reason, right? So that's the point. If you choose around points randomly from the curve, there are many points, not only this one, but already the whole curve is consisting of many points. These are all points already on the curve. We can't choose them and say which one gonna be our solution, because we don't know which one will be the solution. Okay, so that's the thing. This, in the only case this one works is that after you choose HP and Q, you should bring the Bernoulli equation. You should bring the Bernoulli equation and make sure whatever answer you get on the left is equal to the one on the right. For example, if it was 20 equals to 20, okay, then you can approve this. You can say, okay, solution is correct, and I can approve this to 2 points. But this one will take too much time, because you are taking 2 points, for example, 1 point and test, the other point and test, and there is no way of this one. And this is just a long way, that is, no one would do it. I think yes. So that's it. That's it for the introduction. This is the thing I wanted to discuss about with you. Now let's go to questions. I think we can go to question. Here we have the first question. What it says? It says, determine the elevation difference between reservoirs A and B if water at 20 degrees Celsius flows through this pipe system from A to B with an average discharge of 0.145 meter cube per second. Consider the minor losses as well. Okay then, we start. This is just normal question. They didn't mention anything about pumps. Just this one to introduce for us the sharp-edged minor loss, sudden contraction. This is sudden contraction, and this is sharp-edged again, and like that. So what we need to do here, let me open this one from the questions. Yes, this one I mean. So what we said, we write the equation as it is. I took the water at 20 degrees Celsius and I wrote the pipes, both of them PVC, so it's fine. Diameter is different, pipes connected in series, I mean. Therefore, let's write the Bernoulli equation. We don't have a pressure there because atmospheric at A and at B is atmospheric too, so both they are cancelled. Sorry, yes. this one cancelled, that one cancelled, and velocity head is cancelled at both. Elevations, we have the elevations given to us. I think here is, no, it's asking about the elevation difference. No, yes, it's not given. Elevation difference. So elevation difference, I should take ZB to the left and take that and name that as delta Z. If we take this one to the left, and it will be delta Z, that one will be equals to head losses. So what are the head losses? I prepared only major, this one major, and this is the other major of pipe 2, in addition to minor losses. I wrote this here, minor losses. Okay, so what we have minor losses, here I wrote, we have sharp-edged entrance. If we check the notes, sharp-edged entrance, yes, here entrance losses, sharp-edged is, where is it? Sharp-edged, it's half. Okay, here it is half. And for exit, sharp-edged is 1. Actually, for exit, they are all 1. If you just notice, it's all 1. So we say half for entrance, 1 for exit. For sudden contraction, as I told you, here it should be area of the smaller over the area of the larger, because the ratio should be less than 1. Smaller over larger. Smaller is 2, which is this one, 250, and larger is 300. I took the ratio in meters or centimeters, it doesn't matter. All they are equal to each other, okay? Even if you wrote it 250 squared over 300 squared, the ratio is same. It is 0.7. Okay then. And so 0.7, I go there for sudden contraction, it's on the right, and I check for 0.7. Here is 0.7 because this is 6 and that is 8, so this is 0.7, and after we read it, it's here 0.1. Okay, so 0.1, that is the sudden contraction. Anyway, coming down, then how much I should multiply each of these K? The 0.5 entrance with the area of this one, which is the pipe 1. Velocity 1, because velocity 1 is just at the location, and at the exit it's same. Also properties of this one, which is the diameter 2 should be used, and velocity 2, I mean. But when it comes to places, we have two options. For example, here we are at sudden contraction, but we don't know which properties I should take, velocity 1 or velocity 2, which means also diameter 1 or diameter 2. What we said is that we always try to be on the safe side and try to make the losses more. So to take the less more, to make it more, we should select the higher speed, which means the smaller area always. So here I selected the smaller area, which is 2. You see, here it is. That's it. Okay then. And try to solve it. This is just a simple problem now. It turns to be simpler, and only solving, for example, for delta Z, I wrote here the length of the pipes, K entrance, exit, sudden contraction. We can take common factors. I wrote it here, for example, I left it to power 5, but I prefer if you would write it same as what I explained last time. If you can do it, it would be easier. Okay? Because this one here I can make it even smaller. How I can make it smaller? For example, when it comes to here, delta Z equals to, I can say this one multiplied by F1 L1 over D1 plus K entrance. Is there anyone else? No, nothing. Then the next one, which is the D2, yes, multiplied by F2 times L2 over D2 plus K exit plus K sudden contraction. So this one is simpler and easier to solve. Okay, this is what I want from you. Always it's better. Anyway, so After that, we solved it because it's type 1. Because it's type 1, therefore what we need to do is to get Reynolds and for both pipes and get F's. There are no trials, it's just as it is. Then try to substitute and get the answer. Okay, that's it. I can put this option here, or I can write it. At the end, the answer will be the same. So yes, if you now check the answer, how much it is, it's the same, 70.872, it is the same. Okay then, what is next? Now, the second part of the question, it says, calculate the required head of the pump and the pump power B to maintain the same discharge Q equals 0.145 meter cubed per second in the opposite direction from B to A. So we are using now the pump to what? To change the direction of the flow. Normally, in normal case, this flow cannot flow from B to A because of the difference we found. Difference is 70. We mean by this difference is that difference is 70. It means if you take a line from here and there, this distance is this distance is the delta Z already. Okay, this is the meaning of delta Z. So how the flow would go from the lower to the higher, we say by pump. This is the thing, by this pump. We added a pump, okay? So one thing will change, the from here, from B, this one will be the entrance and the left one will be the exit. Okay, this is the first thing. Secondly, for minor losses we mean. Secondly is this one here, it will be sudden enlargement, not contraction. It will be the opposite, enlargement, okay? So all this should be taken into consideration. And also they gave us the loss due to pump fittings as 1.2 meters. Because it says it's meters, it is ready as a loss, okay? So don't multiply it by a velocity head, v squared over 2g. And if you write the equation now, from A to B, just what we solved it before, from A to B it was the difference, sorry, what is this? Yes, it was 70.87. So now if we will make it from B to A, it will be negative 70, because we will be already under that one, so it should be negative. So we can write negative 70. So now what we are trying to say is that you are already, for example, head A equals to head B plus the head losses. I'm trying to make it simply for you to understand what I mean. So how much it was, if we take the difference in both heads A and B to be equals to summation head losses, this difference was how much? 70. So it was 70, this answer, 70 point something equals to head loss. Okay, now what we are saying is make it the opposite. Head B, which is the lower, should be equals now to head A, which is the higher, plus the head losses. So so A is the greater. So if you now put head B minus head A, it will be now how much? Equals to summation head losses. It will be negative the delta Z. Negative the delta Z, already we were having it. Okay? Equals to summation head losses. So negative 70. We mean by that negative 70 equals to this. Anyway, that is the point. as if you are saying, for example, it was, as if you are saying it was 100 and the other one it was 20, so 100 minus 20 it was 80, but then we want the flow to be from the 20 to the 100, so that it will be 20 minus 100 elevation, it will have a minus 80 difference. That is the thing. Okay, then what is left? So negative 70, but we have what? We have a pump. So we have a pump, so it will be added to head B. So it will be negative 70 plus head of the pump. This head of the pump should be greater than 70.87, so that the flow can reach to A. If it wasn't greater, flow will not reach to A. So equals to this one as I wrote it here. Actually, we have here sudden enlargement. This one, sudden enlargement, we should check it. And it is 0.25 over 0.3, the same ratio, but just we should check the sudden enlargement. Here it is sudden enlargement. We should check the sudden enlargement curve. If we come here to 0.7, actually it gives us the same in sudden enlargement, 0.7. If we try to read it, it will be again same, 0.1. It's same. Okay, so for writing, I don't prefer this type of writing. Okay, just keep it. Let me write it or. I prefer this way, or as I did here. Yes, this one minus 70 plus head of the pump. This now 1/2, it will be the entrance. Let me check how we did the entrance. Yes, this 1/2, it was entrance. Now this one should be the exit. Exit belongs to and what I mean is that if we try to write it first like this, no. What I mean is that this one is the velocity head. This is, let us write it just above it. This is velocity 1 squared over 2g, isn't it? And the other one here is the velocity 2. So now if we look to the system, 1, it is related to exit, pipe 1. If you check here the exit, because flow is flowing in the other direction like this. So this one is related to exit, pipe 1. So I should add the exit minor loss. How much is K exit? K exit, it was 1. So I should add 1 to next to velocity 1 here, this one. So here it should be 1.0. Okay, this is exit. Exit, okay. And after that, what do we have? There at the right, we have 0.5. What was it? Here, this is 1. Let's delete this now. I'm not writing it. Here we should put entrance. Here we should put not exit, it should be entrance. Why entrance? Because here if we check at the pipe 2 properties, here we have an entrance. It is not exit anymore. So I should put the entrance, which was 0.5, because it's sharp edged. Okay. In addition to that, we will check for sudden enlargement. Here we are having a sudden enlargement. What about the sudden enlargement, guys? Sudden enlargement, does the area change? We say the area will not change for sudden enlargement. Why it will not change? Because that when we say about sudden enlargement or sudden contraction in such places, we said we should take the smaller area, which has the higher velocity. So smaller area and higher velocity, this one will not change if we change the flow direction. Still, 2, it has the higher speed and the smaller area as well. Okay, so I would still add it here plus 0.1. okay, just the factor, make sure it is same, that one, the blue one. Okay, that's it. So at the end we find the answer. That's it. And we find the answer for HP. It is 141.63. This is it. Actually there, I think we didn't change it. There is something wrong. No. There is still. Yes, in addition to losses, we should add 1.2 here in this equation. What is this 1.2? We can say it easily. It is the head loss due to pump fittings, as they mentioned it in the solution, in the question, I mean. Okay, so that is the head of the pump that we need, 142.83. So for example, this one is too much, but because of the discharge, this one to deliver, you can say to deliver a Q equals to 0.145. It's 0.145 even meter cube per second. It's too much. It's too much because it is equal to 145 liters per second. Okay, required to overcome the elevation errors and provide water at. Anyway, so coming to power now. Power, how much is it? It is power of a pump is given as gamma Q HP multiplied by head of the pump divided by efficiency. This one is the efficiency. So you know, as mechanical devices, it has a certain efficiency, for example 85%, 90%, 70%. So it was given to us in the question, we put everything and we found it. Okay, if gamma is in kilonewton, so the answer will be in kilowatts. Now coming to another important thing in pumps, which is pumps can be connected in series and can be connected in parallel. So what does it mean and how it affects? So we say if you need to increase the head of the pump, if you need to increase HP, you should put pumps connected in series. For example, go back to our sketch, this one. For example, after I have put the system, after I have bought the pump here down, for example, I just discovered that this pump is not working well. It's not delivering the water. Water is just stopping here, for example, at this story. So what I can do is that I can put another pump next to it in series, so that water will be delivered. Water will go and will be delivered to the surface there. So this is the aim. So to increase what we say is that to let the water reach to a higher, to increase HP, head of the pump, we should use pumps in series. Okay, so that is the thing. In parallel, what we say, if you need to put pumps in parallel, that means you are increasing the discharge, not the head of the pump. We are increasing the quantity of water. Okay, so pumps connected in parallel will increase the discharge. So when table is given for the graph, if we are solving for curve or graph, by number of pumps connected in series, in parallel, here for example parallel, I should multiply the Q. I should multiply the whole table, not only the Q, I mean the whole table here, the numbers we have it. But when we have pumps connected in series, we multiply only the head of the pump by that number of pumps. Okay, but when it comes to the equation, normally pumps has this type of equation. Okay, this type of this one we call it pump equation. Okay, so normally we will have numbers into this. So it will be, for example, 15 minus 3000 q squared, and this is just an example. Okay, let me make it this. Anyway, so, and if we have pumps in series, what it affect the equation, we only multiply the whole equation by number of pumps in series. So if they were 3, we multiply it by 3, 15 will be 45, 3000 will be 9000, and it's done. But when it comes to parallel pumps, the equation, it has a special thing, that is, we only divide the right side, which is next to Q, the Q factor, or here, this one, by number of pumps to the same power of Q. For example, in this case, how much is gonna be? This one I should divide it by 4 to the power 2. Okay, this is the thing, 4 squared. Okay, so that is the thing. For example, let's take another one, pumps in parallel and in series, 3 in series and 2 in parallel. For table it will be 3 for the head of the pump and 2 in parallel, so 2 in for the Q. And how is the shape will come? It will be something like this. This one we call it 3 in series and 2 in parallel. Be careful when it comes to parallel. We count only this line. This line is first line, and this is the other line. So there are 2 in parallel. Okay, and then repetitively in the same line it is series. These things. So this is how it affects the table, and this is how it affects the equation. Equation should be multiplied by 3 first, which is 3 in series. Then the Q side should be divided by 2 to the same power of Q. Okay, if you like the numerical problems, numerical samples, I mean examples, we can put it 3 multiplied by 15 minus this much divided by how much? 2. Yes. So that's it. 45 minus this. This is how it will become the equation. Okay, for such a system. Okay, then coming now to this example. This one, I think, on the curve. We will take this only this example. We will take it for the curves, and then I will give you another example, and we can end up the chapter. Yes, I think because the others already, this one is more than enough. Only this example we have. Then turbines, then this one extra for you. Okay, then let's check this example. What it says. It says 2 reservoirs are connected by a single galvanized iron pipe of length something, and then phi is 25 cm, to discharge water at 20 degrees Celsius between reservoir A elevation 70 and to reservoir B elevation 84. So B is higher, and we are trying to take it from 70 to 84.5. So already now he will say, which is not, I think, yes, now it will be coming. The estimated total minor loss coefficient due fittings, elbows, valves, etc. it is 19.8. This is summation K. Here I wrote it, summation K. And they said galvanized iron. I have put the KS for galvanized iron. Length and diameter I wrote it. Then it says definitely pumping system should be installed to allow this flow to occur within the system, so as to help for carrying water from lower reservoir A to the upper reservoir B. check the possibility of a single pump. This is the first example. So what is the table for the pump? This is characteristic of the pump, this one. For example, if you want to deliver 5, pump will give you 12 meter high. It can deliver it up to 12 meters. Then if it is 15 discharge, it will be 12.50, like that. It is just given and according to efficiency. So we are trying, this is the sketch. Now we write the Bernoulli equation. Directly when you write the Bernoulli equation and say we have a pump and we added the pump effect, we can check that 70 plus H head of the pump equals this one plus head losses. We have 70 minus this one. How much it's gonna be? If we try to put the head of the pump at the side, at one side, how much it's gonna be? It will be 14.5. So 14.5. Go and check in the this 14.5 in the table. Do we have 14.5 here for head of the pump? No, we don't have. We have how much is the max? Maximum is 12.5, this one, isn't it? So maximum is 12.5. So is one pump, we can ask now this question, is one pump is enough to deliver water there? No, we can say that water will not be delivered there. It cannot reach. Okay, water will be somewhere here, for example, because this sketch, we know that it's not totally true. This one means this elevation is higher than that one, or already the flow will be the opposite. It will go like that. Okay, so it's easy. We can say maximum HP is 12.5 from table, hence single pump won't be enough. Okay, 14.1 greater than 12. So second part, it says determine the power P consumed by the suggested pumping system, which is two identical pumps in series. Now we are using two in series. By the way, from the beginning, because this one is just yes, because this one is what we call it. Okay, because this one is a curve problem, we will use the curve to solve it. From the beginning, you can sketch this graph. And by the way, these numbers will be, I will cancel them. These will be 5, 10, and then the other one, how much? 10? 5, 15. No, it's here, it will be 10, and then that is 30, so 15. Then after 15, what we have? 20, and so on. Okay, this one, I mean, if you draw it from the beginning, because in the exam you will take the question and you will draw, for example, directly you will draw the pump curve. So what we can do is that now after we know that we need another pump in series, shall we draw again another curve and say it will be something like this because it's series and blah blah? No, what we can say is that already I will hold this one, for example, and say just because two in series, because they're gonna be, sorry, we said two in series, HP, this one won't be applied to this one, sorry, this one, it will affect the head of the pump because series. These numbers will be 2.5, scale should be 2.5, then 5, then how much? 7.5, 10, and so on. Okay, this one should be like this. 7.5 and then 10. So what do we mean by this one? We mean that when we come down here and we discover that it will be series, 2 in series. 2 in series, what does it mean? HP means the y-axis should be multiplied by 2. HP, head of the pump, should be multiplied by 2. 2 series means 2 HP. So what we will do is that we only cancel the old ones, these ones, 5, 2.5 and 5 and like that, and we should just make it double, so multiply by 2. Each is just multiplied by 2 at each point. And graph will be the same. Graph will be the same, just multiplied by 2. That will give you this scale, new scale. Okay? 5 multiplied by 2.5 is 5, 2 by 5 is 10, like that. So curve, this one, the blue curve, will not get affected at all. Okay? On your drawing, even on paper, you just by eraser, for example, you take the eraser and just delete, for example, these numbers and update them. Okay, that's it. That is what I wanted to tell you, because it's important. We are not drawing the charts again, only one time. Okay, then 2 in series we updated. You see here the scale is different now. Otherwise, if you draw from the beginning, the scale will be like this: 10, 7.5, 5, 2.5. Anyway, about the scale, you should select 30. I mean, a certain scale you should select it, because according to Q and HP, according to these, especially for HP, the Q is already fixed, but the other one you should say you can take the difference of 1 or difference of 1.5, 2.5. Here the Excel took 2.5 difference for the scale. Anyway, this is our Bernoulli equation, 14.5. We said how we found it, the difference, and I have put it on the right so that HP will be ready to calculate, because we will be calculating or solving for HP. So head losses, we have FLQ squared over 12.1 d power 5 plus the minor. If we take the common factor of this one, velocity head, it will be something like this. If you put the numbers, it will be something like this here. And what are the unknowns? Q and HP. Okay, Q and HP. So now we can get any answer, any assumption. I can assume 30, for example. Here I think we have assumed, no, we have assumed 35. So assuming 35 Q, which is, be careful with the units, which is 0.035 meter cube per second. So substituting this meter cube per second in Reynolds, try to get Reynolds, and then get F. That's why I told you there is no trials. There are no trials because we are assuming Q, so you can directly get the real F, which is based on Reynolds. After that, substitute it in Bernoulli. Here it is. We substituted it in Bernoulli. And solve for HP. HP now it's 22.14. So 22.14 it is somewhere here. And 35 it is somewhere here. So it is kind of on the curve. It's not totally on the curve, but kind of on the curve. That's why I said if you check it a bit, it's a bit higher than the curve, isn't it? So I can take another one, say 34, get the Reynolds, get F, substitute in the equation, 21. Now it's a bit below. Anyway, we can just say it's fine. So we were lucky. If you are lucky that much and from the first trial you can, or you could, for example, get the point directly on the curve, that's perfect. That's correct. You can't say anything. And we can't say anything, to be honest. Okay? So what is next? Next is, they said, in this part, they said, determine the power consumed by suggested pumping system. By 2 in series, they mean. So how I can find the powers consumed? I should find the efficiency, because now we know the head of the pump, and we know this charge. We need what? we need the efficiency. You can do the interpolation. Be careful. We can do interpolation for efficiency, but don't say, for example, now we have a head of the pump 21.73 and you will go and try to make interpolation between this one 21. There is no already 21 here. You should get the latest table. What is the latest table? It is this one, the one we modified it. Here, this one, it was modified with 2 for HP, which means 24, 25, and like that. We multiplied it with the first table. Okay, so this one, as I told you, yes, this one, and then you can bring the efficiency. You can bring the efficiency table. Efficiency won't be multiplied by anything. It's just written here under each one. It will be written, and you can you can get the efficiency like this. Okay, so efficiency table, it is not affected by any number. Okay, you just directly interpolate. Okay, then what is next? Here what I wrote, the 23 and this one 21. Yes, so either by using this one here, I have used the head of the pump and the efficiency. So either you use or the efficiency, it is here. Okay, or the efficiency. On the right side here, I use the Q and the efficiency. You can do the same. I mean, for interpolation, you can use whatever you want for interpolation. Okay, all will give us the. It will be a bit different in the interpolation. If you interpolate the head of the pump, would be better than the Q. If you don't want, it's okay. Also, you can do it both. For example, here we said 34, so 34 it is somewhere here. It is somewhere here, 34, and at the same time you may use 21.73, which is again somewhere here down, isn't it? 21.73. Okay, so that's it. What else we have? Then we substitute and get the power. For example, here 3 in series. The thing, we modify HP again. As I said to you, this scale, whatever you used as a scale for y-axis, it won't be changed. You only multiply by 3. The first one you draw, you multiply it by 3. Okay, and then what we said. Yes, this here I explained this way, the one we were talking about, taking 1 point and check it. As I told you, if you take 1 point and you check if they are equal to each other, then perfect, but they are not. Okay, that's the point. So let's check. Trial 1, I selected 35, and you see now 35 is way less than the curve. It is way less than the curve. If we go together, if you want, we can go together and check. For example, this if this is the way the curve would go, then this point will be our solution, 45 or something. Let's check if I am correct. This one, it can be, we can do it somehow at some cases, and it can work. So 35, I checked. We said we got F and we got everything. It's not correct. Then 40, we took 40. How about 40? Not 45. It's here. If I copy here this one, no, not this one, only this curve. I want to see if it is going on the same line. Yes, somehow we did it correct. Yes, 45 will be the answer somehow. Let's check down. 45. It is so close. You see, if from the beginning, if we chose this one this one 45 as a trial 2, it will be better for us, because then this will be cancelled and we will check that it's a bit below the curve. Then we will do the third trial. This, instead of fourth, it will be third, and we will get the answer. That will be better. But here we said we needed 46. By the way, for trials of this by curve, if you are solving by curve, you should do the trials fully, all the trials. You can't say I will stop at the third. You should do the trials until you put the point on the curve. Or, by the way, you can do something like we were saying. For example, trial 3, it was 45. It is a bit below. What you can say is that it is on the curve. You can do it like this. Okay, that is, don't do it in the exam. So this one will be directly 0. So don't say it's on the curve and make the point that much huge. Okay, so that's it. But some students still they do it. So last trial we said 46, and again we checked. Now it is on the curve, exactly on the curve, you see. Now it's perfect. Again, for the trials here, for the efficiency, because it's asking about the efficiency percentage. Again, we said I used here HP. We prefer the HP to be used, and this line is the efficiency line. Okay. Then we found the power. That's it. Now in this, by the way, in this one, how we explain it? You see this? Okay. In this part, when it says about using 3, I think. If another bump 3 in series in identical, it says what is the percentage of increase in Q and power in this case, in the third case. So what we do is that we take the power. Here it is. I will explain to you. Yes. For 2 in series, the discharge it was 34. This one, discharge it was 34. For 3 in series discharge, it became 46. So for the percentage increase, what we say, 46 minus 34 over 34, because this is how we are going, I mean, in the system. So 46 minus 34 over 34 times 100, it gives us the increase of 35% in discharge we have. And in power the same. Power, it was at this one, the power it was 16.4 kilowatt. Okay, and at this one the power it was no, sorry, it was 9.03, and this one is more, like 16.4 exactly. So like that. Now when it comes to this part, what it says we have 2 in series and 2 in parallel. If 2 and 2, therefore you should modify in this case 2 for the discharge and 2 for the head of the pump, and this table will be updated. Okay, again, as we said, you should only, the first curve you draw, you should only cancel this. And in exam, by the way, you don't have that much parts. It will be 1 only. So you just first curve, you cancel these and you multiply by the number. For example, 2 for x-axis and 2 for y-axis, for the scale, I mean. Or instead of cancelling, you just write next to it. Okay. So first trial here we said let's take 50. I just said 50 because the curve gets smaller. Okay, 50, I found it, it's way above the curve, it's too much above the curve. So if we draw a line, it will be something like this, hopefully, if the path is like this, maybe 40 something, it will be the solution. I can check it now, 40 something. So let's check it. 40, I checked, it's on the curve exactly. You see how you can expect. What we did is that I did try to do it like this, or something like this, and then I discovered it's something close to 40, So directly I can expect this, but it seems it is more like this. It's going, yeah, it's something like this. Oh, like this, yes. So that's why you can't make sure how it goes, because you don't know how it is, like a very going like this, so wide, or it's directly sharp like this, for example. So we can't know this, but we can try to approximate it. Point on the curve, we are done. Again, they are asking about percentage of increase according to previous one. So we found it again, the same thing. That's it. That was for the whole question, the question before. Okay then. Coming to turbines. Turbines is so easy as a problem, as a type of device. Turbine is sometimes the water counter that is placed on for our flats or in everywhere. And turbines, they are we said pumps, they are increasing the energy. This one, it decreases the energy. The turbine, it decreases. Okay, so we will put it minus. The only difference, we will put it minus in our equations. Okay, so minus head of the turbine. For power of turbine, it is efficiency gamma QH HT. So here, for example, I have a simple question. It says the turbine shown below in the figure facilitates or generates a power of 72.8 horsepower. Determine the cast iron diameter. It's type 3 problem. Length is given. The average discharge is given. So find the efficiency of turbine is 87%, and it is estimated that entrance loss is 0.25. Water elevation is given. Everything is given, and they are saying 1 horsepower is this much watt. Okay, so if we try to write the Bernoulli equation from here to the exit, and there is no pressure here and no velocity. Here we have velocity and we have elevation, and we have elevation there. We should put minus head of the turbine. And we have wrote the equation. Everything is written with the K entrance and simplifying the equation. For now, I'm trying to go a bit faster because things are getting repetitive, so you can directly understand what's going on. There is no need to explain everything in details in every example. Okay, that's why I want from you to study hard, even for the previous chapters, so that when we reach to such chapters, there will be no problems. Okay then. So when it comes now to the Bernoulli equation, we have two unknowns: head of the turbine and the diameter, because it's diameter problem, type 3 problem. So we can say that already the power was given to us. But it was given in horsepower. It says 1 horsepower is equal to 745, and we have a 72.8 horsepower. So 72.8 horsepower, how many watts it will be? You can directly multiply them, so it will be something of this much, 54,000 watts before we multiply. Okay, then after that, if we multiply it by, we say multiplied by 10 power minus 3, how much it will be? It will be 54.2 kilowatt. Then since the power is given, we can check the power equation and try to find the head of the turbine, this one, because efficiency is given. Efficiency, even they mentioned it in the question. They said efficiency is 87. Here it is, 87%. So we found the head of the turbine, and it will be in meters. Then we will be adding it there. Then the rest of the question is just a type 3 problem, normal solution. Okay, that's it. Yes. Okay then, here we have another example. I wanted to solve it with you. what it says, this is a sample example. Water at 17 degrees Celsius is pumped from the lower reservoir A to the higher reservoir B. This is the sketch. That is A, it is pumped to higher reservoir B. Okay. With the help of the pumping system, pump's connection details is given separately as an enlarged form. Okay, like this is the pump, but it is this one, zoomed in, let's say. Okay, the below given figure is the schematic representation and not scaled, but coordinate axes are proper. Consider the given minor loss coefficient K values and note over the system, and the pipe diameter is 40 and it is made of commercial steel. The system functioning under absolute atmospheric pressure 101. The single pump characteristic is also tabulated below. Determine the flow rate that satisfies the below given, then the power, then maximum topographic elevation just before the pump. Anyway, for no cavitation for sure. Okay, and also they mention the distance, same as before. So here you have this one, for curve, if you are interested in solving with curve, and we have also the equation. Okay, we have also the equation. So you have first option to solve by curve, second option to solve by equation. Here we solve it in both cases. Okay, so we will discuss it now. What is the first thing? How to start to solve? If we try just to write the Bernoulli equation, what is the Bernoulli equation? Here we have 24 gauge. It seems it's gauge. It didn't write. It should be written, by the way. Anyway, 24 gauge divided by gamma plus. There is no velocity head. There should be an elevation. What is the elevation? It is not specified. So what I can understand from this, I can understand that there must be a datum line. I will try to make it this one. Is it possible? Yes, it can be. Then I would say this is the first elevation, that is the second elevation. First elevation, so it's gonna be 1.5 plus 7 equals to, try to write the three elements there. We have 78 over gamma, sorry, plus there is no velocity head. What is there? There should be the elevation. What is the elevation up to there? We can say 1.5, this one, 1.5 plus 10.5, yes, and 2.8. That's it. 1.5 makes me here in the center of this pipe. Then 10.5, then 2.8. So always try to simplify the problem. Look, I am not, you see, now I think when you are watching this sketch of this problem, you would say it's so hard. But look how we are solving it. For example, I'm solving, I don't care about any other details. My eyes, they are not on the other details. My eyes only on the elevation. I care about only now finding the elevation, and then now start to look for other details. Okay, so other details such as what? We wrote the main things now. We have pump, so I should put plus head of the pump, right? This is important. Then what is rest? Rest is to write the head losses. So what I would say, I would write the major loss of pipe 1 and also pipe 2. Actually this one should be considered as one pipe, 105, and the other 165. It can be considered as one pipe. It will hold, it will carry the same discharge. So what I can say is that F1 multiplied by L1, and directly because we are writing everything, L1 how much it is, 105 plus 165, to make sure what length 1 I mean, because there is nothing specified. Diameter 1 multiplied by velocity 1 squared over 2g plus. Now that pipe I will consider it as another pipe, the vertical one, F2 L2 over D2 multiplied by velocity 2 squared over 2g. Okay, plus what is the next? Starting with minor losses. Firstly we have K entrance, so K entrance multiplied by which velocity it should be? Velocity 1. Now next plus by the way, you can write the losses on the other side, just the minor losses. Then we can take the, anyway it should be on one line. Then what is next? Summation K pump. What does it mean, this summation K pump? There is a minor losses of the pump, for example. Summation K pump multiplied by velocity 1 also. Velocity 1 or 2, it's the same diameter we have. This diameter is same. Okay? By the way, all the diameter is same. Even that one, that portion. Then why I didn't take the summation of all the pipes? This one, to consider it as one pipe for major loss. Why? Because easily you would tell me that here at this point there is a water loss of 6.5 liters per second. That will make this discharge different from that discharge coming here. So I should name this one as Q1 and that one is a Q2. So that is the reason. But later on you will see it. Okay. So after summation K pump, looking for another minor loss, KT. Okay. So here we have a T. So KT multiplied by velocity. Which velocity we said? This one here actually we said higher velocity and smaller area. So higher velocity will be which one? Which one will be with higher velocity? Same area, they are both same area, but here we have a loss. So we expect the first one to be with higher velocity, isn't it? Because here we have, or think of it as a quantity, not as a velocity. Q squared over 12.1 d power 4. So because here we have Q1 and Q2, diameter is same, we have Q1 and Q2, and we know that Q2 is gonna be less than Q1. Or let's make it the opposite, greater than, easier to read. Yes, greater than Q2. Therefore you would what? You would prefer to multiply it by, or we have to multiply it by velocity 1 squared over 2g. Okay? So this one also keep it in mind. This one for this. Anyway, what is next? After the T we have valve. We have plus K valve multiplied by it should be velocity 2 squared over 2g plus K exit multiplied by velocity 2 over 2g. That's it. Okay, if we think of taking common factors, let's think of taking common factors. This one also we can make it smaller. This one will be minus. So here I can write this one minus 78. And this one will be minus 114.8. Yes. So firstly let's put a spacing here. Okay, F1 firstly, not F1, sorry. Velocity 1 squared multiplied by, we have F1 L1 over D1 plus, where is the other one? K entrance. Where is the other one? Summation K pump. Where is the other one? Summation T, KT. Yes, so this one is done, the pump, the T, K entrance, and this one also. By the way, still we have these next to it. next to this one. So after this I would put plus velocity 2 squared over 2g open bracket and say f2 L2 over d2 plus the rest, k valve plus k exit. Then the rest is just deleted. Okay, you see how simpler it became, and even we can make it simpler and simpler. Okay then, this one for example, I can calculate it. This one I can calculate gamma. Still we can substitute later. So it's like this. After this we can put this one, the q, turn them into q, both of them, q1 and q2. Especially we made them q1 and q2 as I told you, because we have to take this one here, or it's, you know, it's just, we did it here because of this one, and we should prepare this one. We can say q1 is equal to q2 plus 6.5, so 6.5 divided by 1000. This is our equation 2. This one we needed to make here only one unknown, which is 1q for example. Okay then, if you would solve it by curve, what you need to is to modify, because here we have 2 in series and 3 in parallel. So we need to modify this table by what? Because 3 in parallel, 3 multiplied by the Q, and 2 in series, 2 multiplied by HP, which is head of the pump. Okay, efficiency we don't multiply by anything. Okay, and that's what we did here. That is what we did. We did the curve, to be honest, but it's not shown in details. We did the curve. Then we should assume, for example, I assumed Q1 as 50. Then I found F1. This is just in quick. Reynolds is there. Then Q2, because in the equation we need Q2 as well. Q1 we got it. We need Q2. So Q2 will be calculated by this one. Q2 is equals to Q1 minus this, isn't it? Minus this one, you can calculate Q2. After that, the only unknown will be HP, head of the pump. So after I solved for head of the pump, it was 12. So it is here. So what I expect, if I draw like such a curve, I should just increase a bit. And instead of 50, I should take it 55, for example. I took 55, still it's not. Look, here it's not same as what I expected. Here it should be wider, and it seems it will be 59 or something. So after that we said make it 59 or 63, even more. You see, it was even more like this. 63, it was the correct. So it was so wide that we couldn't expect. I expected narrower, it is wider. Anyway, that's the operating curve. So, what we said last time. So yes, in trial 3 it was 63 assumed, and then we got Q2, and after we got Q2 from the second equation, you substitute the discharges we have, as we said, and the F's we already got them. Then HP is on the curve. Yes, I say this is the HP, correct. So this is, if they ask about the power, we can get the power. But the thing is here, what I want to show you is, because sometimes drawing this chart is taking time in the exam, because you will have a millimetric paper that is like this, and with all the lines and blah blah. So it's not easy. We can solve by equation. The aim of this example to show you the equation. So here we said we have 2 in series and 3 in parallel. So 2 in series, I should multiply the whole equation by 2. Then 3 in parallel, I should divide this 10,000 by 3 squared, same as what I did here. 3 parallel, so 3 squared. 2 squared. Why squared? Because it's same as the power of q. So this is our equation, our pump equation. You see now what I wrote here? This is our first equation and how I simplified it. So instead of HP, I should only substitute, the only difference is only substitute here this number, 21 minus 222.22 q squared. Which q it's gonna be? Here, by the way, it's gonna be q1. Why I selected the q1? Because if you check the question, what is passing in the pump is discharge 1. Here, discharge 1 is coming, so it will pass from the pump and it will continue. That is discharge 1. But discharge 2, it has no relation. Okay? So that's it. Be careful. And therefore, you can directly, after we substituted here, we took everything according to the, K valve, everything is just substituted. What you can do is that we said how many unknowns in this. Now the solution will be so easy. It will be like the other examples we were solving before, which is like there is no pump, for example. Q1 and Q2, we have two unknowns in the Bernoulli equation. I cannot solve it. What I say, we have continuity. This is the second equation. We have a second equation. So from second equation, you can say Q2 is equal to Q1 minus this much. So substituted in Bernoulli equation instead of Q2, instead of this one, it will become this. And be careful with the brackets. It's the square here is on the bracket itself. So how you can solve this equation? Now, first equation it was. How we can solve it is just a type 2 problem. It's totally a type 2 problem with discharge unknown. Okay? So what normally we do, we assume fully turbulent flow, get F1 and F2. Why they are same? Because we have same diameter. And we are assuming fully turbulent, so this charge difference we are not considering it. Okay, we are just considering only the pipe diameter and properties, Ks over d. Then we solved the Bernoulli equation. I got this answer for Q1. Then Q2 by continuity, I can get it. I got the Q2. Solving for F1 and F2, they are not equal to the previous ones. Do another trial, and then in the second trial I got the F new equals to F previous, old ones, and therefore I can say discharge in 1 it will be this one, discharge in 2 it will be this one, which is exactly similar to the previous one. Even by equation you can get more specific answer, because in the previous solution we got 63 and we don't know that dot how much. We just said 63. Here you can know that it is 63.23 liters per second. So it is more precise, more detailed results. Okay? And later on, if you are interested in finding head of the pump after you have finished, what we can do is that we can just substitute the Q1 into the pump equation, and we can get it. This is in meters, by the way. Then we can find the power. So that's it. This example is so good, so important. You can solve this one. Try to solve this one, and I want from you to solve maximum topographic elevation. Or no, this one. No, this one can't be solved. Only you can change it to check the cavitation occurrence before the pump. Before the pump, yes. I want from you to check that. Cavitation occurrence, yes. As a homework. I think that's it. If there is anything else we can discuss here in the notes. In the notes we solved. There is one extra question after the turbine. You can have a look at it, and later on I will give you another example about pumps in case of a parallel, which means like this. If we have a long parallel pipe and the long parallel pipe from here, then it continues and we have a pump on it here. Okay, if we have two pumps, and that will be a reservoir, yeah, for example. Okay, that needs also a special solution somehow. That's it, I think, for this lecture. If you want, we can include that one, but I think no need. Later on we can take it as a tutorial. Okay then, thank you for understanding and attending, and see you later for chapter 5.